Hello, and welcome to another online lecture for Psych 671 that covers regression and research methods related to that. So this will follow up the the first lecture on continuous interactions. So today we'll kind of talk about a few more things that we need to do when we're running regressions with continuous interactions, and then we'll go through some examples in SPSS, JASP, and R. So if you want to follow along in JASP and R, you can. So you'll have the data set there and the R script that I sent out at the beginning of the semester. So picking up from the last lecture, we talked about interpreting the different slopes and how we can interpret B3, the interaction, in one of two ways. So treating one of the variables as like the proximal predictor, that we're really focused on that variable's association or correlation, say, with the dependent variable. And then the other predictor is the contextual predictor. So in terms of these lower order coefficients, I think, again, I want to reiterate, when you have a higher order term like an interaction term or a curvilinear term, a quadratic term, when you have that, then you can't just interpret those lower order terms as you would if there wasn't a higher order term in the model. So it doesn't mean anything about the general effect of that variable like it would, say, if you're just looking at the correlation between one variable and the outcome variable. It only specifies the relationship about that variable when the other predictor in the model equals 0. So B1 is the simple slope for predicting y from x1 when x2 equals 0, and then B2 is the simple slope for predicting y from predictor 2 when predictor 1, x1 equals 0. Okay, so in our example, B1 was the simple slope for predicting satisfaction in social life from extroversion when number of people talked to equals 0, and then B2 is the simple slope for predicting satisfaction in social life from number of people talked to when extroversion equals 0. So it's the relationship when that other predictor equals 0. So how could we make B1 and B2 describe more interesting values of x2 and x1? So if you're in a class, I might ask this as a question and then see if anyone knows. So does anyone know? Okay, hopefully you might have thought of centering. So centering can make our 0 points more interesting. So recall that in polynomial regression we center x, so the simple slope describes a point on the regression curve that we care about. So there we are interested in looking at those simple slopes, say for a low value of x, a middle value like the mean, and then a high value of x. Okay, or we could center at a theoretically interesting value. So we could center at like a clinical cutoff score, or a value that's just been really focused on in a particular literature or something like that. But often, as a default, we just center at x at its mean if we don't have any other good reason for centering x at a different value. And then typically we center x at more than one value and then rerun the regression to give a more complete look at the results. So this is because interpreting the quadratic coefficient itself isn't really easy. So it's much easier to break it down by looking at that lower order relationship at different points for that predictor. So we use this same basic approach, namely looking at simple slopes when we do regression models with interactions. So in a regression model with an interaction, what we do is we center to make B1 and B2, and then of course also the intercept B0 describe points on the regression curve that we actually care about. Okay, so rather than centering one predictor like we do in a polynomial regression, we now have to center both predictors. So we can center at theoretically interesting values like a clinical cutoff score, or by default a lot of times we just choose to center at the mean. Okay, and then once we center both predictors, we typically want to center at different values for just one of the predictors and then rerun the regression. So what we're going to do, and I'll go through this and more, is we're going to center the contextual predictor at different values and keep the proximal predictor centered at the mean. So since the other predictor, when its 0 point changes, that describes something different about the predictor that didn't change. So we'll get more into that. So we can center x1 at its mean and then run the regression with x2 centered at different values, like the mean and plus or minus 1 standard deviation. So note again, this is 3 separate regressions. The mean is one regression, and then centered at plus 1 standard deviation above the mean, and then 1 standard deviation below the mean is another separate regression. We could also do the opposite case, center x2 at its mean, and then run the regression with x1 centered at different values. Okay, the mean plus and minus 1 standard deviation. And we only need to report one of these approaches. So how do we decide which one? Okay, so the question is just the same as the question of which interpretation of B3 to report. So the predictor that is more proximal, the one you're really kind of focused on, should be kept centered at its mean. And then the predictor that is more contextual should be centered at different values. So the mean and plus or minus 1 standard deviation. So when we center this contextual predictor at different values, it's going to tell us something about the relationship between that proximal predictor and the outcome variable at different values of these contextual predictors. So say at the mean value of the contextual predictor, at a high value, 1 standard deviation above the mean, and then at a low value, what is the relationship between that proximal predictor and the outcome variable at those different values of this contextual predictor? So say we make number of people talk to the proximal predictor and then extroversion the context predictor. We then have 3 regressions to run. Number of people centered at the mean, extroversion centered at the mean, number of people again centered at the mean, now extroversion centered at the mean plus 1 standard deviation. And then number of people centered at the mean, extroversion centered at a low point, the mean minus 1 standard deviation. So the interaction term is always made by multiplying the terms after they are centered for the model. So this point is again important to reiterate. So just like in polynomial regression, we had to create like a new polynomial term each time. Here we need to create a new interaction term by multiplying the values when they're centered at different values together. So if we look at our results for the whole model, our R squared is 81. So that's really good in this made up data set. And then if we look, so that was the uncentered model, and then at the mean centered model, we get the same stuff for the overall model. So centering doesn't change R squared or its f-test, it'll just change the coefficients, mainly for the coefficients of the other predictor that you didn't center at different values. Okay, so here's our uncentered model, and then here's our mean-centered model. Okay, so the highest order term doesn't change with centering. Okay, so here's the mean-centered model again. So B0 is the predicted satisfaction in social life for a person scoring at the mean on extroversion and the mean on number of people talked to. So the mean is a better representation of central tendency than 0 in this case. I think number of people talked to had at least 1 to 13, so 0 wasn't even included. So it's a lot better and more meaningful to use mean-centered data in most cases. Okay, and then B1 is the predicted change in satisfaction in social life for a 1 unit increase in extroversion for a person who talks to the mean number of people. Okay, so in the context of this other predictor, when it's centered at its mean, so number of people talked to is at its mean, then this is the slope for extroversion and how it predicts satisfaction with social life. Okay, and then B2 is the predicted change in satisfaction in social life for a 1 unit increase in number of people talked to for a person who is at the mean of extroversion. So in the context of extroversion being centered at its mean, this is the slope predicting satisfaction with social life from number of people talked to. Okay, so basically each person you talk to, it increases about half a point on that satisfaction with social life score if you're at the mean value of extroversion. So again, if you're not at the mean value of extroversion, maybe this slope is much different or much lower. So if you're more introverted, number of people talked to doesn't have as strong of an effect. If you're more extroverted, the number of people talked to has an even stronger effect on satisfaction with social life. Okay, and then B3 is the change in the simple slope for predicting satisfaction with social life from number of people talked to for a 1-unit increase in extroversion. Okay, or we could say the change in the simple slope for predicting satisfaction with social life from extroversion for a 1-unit increase in number of people talked to. Okay, so we're considering this interpretation. We're not considering the second interpretation because we're treating number of people talked to as the proximal predictor and then extroversion as the contextual predictor. Okay, so say if extroversion is 1 unit above its mean, then the simple slope for predicting satisfaction with social life from number of people talked to is 0.546, okay, plus 1 unit times 0.013 equals 0.559. Okay, so that would then be the slope for predicting satisfaction with social life from number of people talked to. If extroversion is 3 units below the mean, then the simple slope for predicting satisfaction with social life from number of people talked to is 0.546, so our coefficient for number of people talked to, plus -3, because it's 3 units below the mean, times that interaction coefficient. And then that gives us a slope value of 0.507. So as extroversion gets lower, that relationship between number of people talked to and satisfaction with social life attenuates or gets smaller. And then as extroversion gets higher, that relationship gets stronger. Okay. So here's our model with the mean-centered values, and then with extroversion at the mean plus 1 standard deviation. Okay, so note that the extroversion coefficient didn't change, the other coefficient changed that we didn't center at different values. Okay, so the highest order term doesn't change with centering, but why does B1 also not change? Okay, so when one predictor is kept centered at its mean while the other predictor is centered at different values, the coefficient for the predictor being changed actually stays the same. Okay, so you might be asking yourself, what is up with this? So this doesn't, appear to be intuitively obvious. Okay, but it's because each coefficient describes the simple slope when the other predictor is 0. Okay, so this might take us a minute to wrap our heads around, but this is kind of really what we're doing when we do models with interactions. So we change something to that contextual predictor, and then that changes the relationship of the other predictor, the proximal predictor, and its slope, quantifying the relationship between that predictor and the outcome variable. So if one predictor is kept centered at its mean in different models, the other predictor's coefficient will be describing the same 0 point, so it's going to stay the same. Okay, so if x2 is centered at different values while x1 is kept centered at its mean, because the 0 point for x1 is kept the same, the coefficient for x2 will stay the same. So that coefficient for x2 is describing something about the relationship between that coefficient and the dependent variable at a specific value of the other predictor when it equals 0. So since we didn't change anything about that other predictor, we didn't center it at different values, the coefficient for x2 will not change. So because the 0 point for x2 is changing, the coefficient for the other predictor, x1, is what's going to change. Because now we're looking at a different context, basically, when that 0 point for x2 is different. Okay, so this might take a little bit to understand. It's a little counterintuitive, but it's really describing what an interaction is. So it's the effect of one predictor. When it changes, that changes something about the other predictor and its relationship with the dependent variable. So here's our mean-centered results again, and then here are our results for the extroversion centered at the mean minus 1 standard deviation. Okay, so we get the highest order term doesn't change with centering. B1 doesn't change because number of people talked to is kept centered at its mean. Okay, so if we interpret the proximal coefficient at the mean level of extroversion, here's the simple coefficient for number of people talked to, so 0.546. It looks like it's significant. P is less than 0.001. At 1 standard deviation above the mean level of extroversion, Now we have kind of an even steeper slope predicting satisfaction with social life from number of people talked to. So since these are all on the same scale, it's perfectly fine to interpret kind of the actual coefficients themselves. Okay. And then at 1 standard deviation below the mean level of extroversion, now that slope is only 0.28. So at a very high value, the slope is 0.81. For a 1 unit increase in number of people talked to, that's associated with a 0.81 increase in satisfaction with social life. But at a low value, a 1 unit increase in number of people talked to is only associated with a 0.28 increase in satisfaction with social life. Okay, and it's not significant in this case. So P now equals 0.066. So if we were writing this up, we could say number of people talked to was a stronger predictor of satisfaction with social life for more extroverted people. At 1 standard deviation above the mean of extroversion, 1 extra person talked to was predictive of a 0.1 unit increase in satisfaction with social life. But at 1 standard deviation below the mean of extroversion, 1 extra person talked to was predictive of only a 0.28 unit increase in satisfaction with social life. So in other words, there's a much weaker effect of number of people talked to on satisfaction with social life the lower you go for, the lower the person is for extroversion. So just like in a quadratic model, centering predictors in interaction oftentimes reduces non-essential multicollinearity. Okay, so specifically now we can, we might be concerned with the correlation of each predictor with the interaction term. Okay, so that'll be reduced when we center. So it reduces standard errors and it makes it easier to reject the null when testing simple slopes. So centering is again a good idea, okay, for multiple reasons. So just to look at this, if we look at our correlations among our predictors, that's pretty good. You know, extroversion, number of people talked to, is not correlated. Actually, this is a made-up data set, but you know, if we made it up again, we might expect a little bit of a correlation. You know, we might expect extroversion and number of people talked to be at least slightly correlated. But anyhow, if we look at each of those coefficients and their correlation with the interaction term, they're pretty strong. Now, I think there's been some work that shows that these relationships have to be really high, like maybe even a little bit higher than this to really create a lot of issues. But still, if you can reduce this non-essential multicollinearity, it's never going to hurt, and it's always going to be a good thing. So if we look at these same correlations now with our correlation centered, doesn't change anything, of course, between the correlation for extroversion, number of people talked to, but it does change the correlations between each lower order predictor and the interaction term. Okay, so now 0.02 and 0.2, so that's much better than these up here. Okay, so those correlations of each predictor's separate effect with the interaction declined with centering. Okay, so that's great. So like with any other regression, we'll also want to look at significant tests for the coefficients. So the coefficient for the center predictor, the simple slope, is the only one that will change from model to model. One caveat, it's not really the only one. The intercept, the simple intercept, changes too because it's still describing the 0 point, but it's typically only the simple slope that we care about. So that's really what we're interested in. If you're used to thinking about correlations and you're just moving to regression, that simple slope is basically what is analogous to our correlation coefficient, or the closest thing in a regression model. Okay, so that's typically what we're more interested in, is that relationship between the proximal predictor and the outcome variable. Okay, so if we look at the interaction, so the interaction is significant. The association between number of people talked to and satisfaction with social life significantly differs across the levels of extroversion. Okay, extroversion is a significant predictor of satisfaction with social life at the mean level of number of people talked to. Okay, so again, it's not describing the effect of extroversion on satisfaction with social life overall, just at the mean level of number of people talked to. And then similarly, number of people talked to is a significant predictor of satisfaction with social life at the mean level of extroversion. All right, now let's look at the number of people talked to at the mean. and then extroversion centered at the mean plus 1 standard deviation. Now number of people talked to is a significant predictor of satisfaction with social life, 1 standard deviation above the mean level of extroversion. Okay, and then at 1 standard deviation below the mean level of extroversion, now number of people talked to is not quite a significant predictor of satisfaction with social life. Okay, so the effect gets attenuated the lower we go for extroversion. Okay, so you could verify this even more if you just wanted to arbitrarily pick out an even smaller value of extroversion and center at that mean. Then this might be even further away from being like a significant simple slope. Okay, so one thing to note is that we'll get to this later, but really when you center at those different values for the context predictor, then you can get kind of all the information you need to get those simple slopes and to tell whether the simple slope is significant or not. So very often, like with an interaction, it might be, well, the simple slope isn't quite significant at this low value, but it is at these two other values. Of course, if it's a crossover interaction, it could be something like where the relationship between the proximal predictor and the outcome variable is positive at low values for the contextual predictor, but maybe it's like negative, the association is negative at high values of the contextual predictor. Okay, so we'll also, what you typically do when you report interactions is that you plot the simple regression slopes to kind of show the effect of the interaction. So if we run regressions with one predictor centered at its mean, and then plus or minus 1 standard deviation, we can then plot the resulting simple regressions to better visualize the results. So we'll want to look at simple regressions of the dependent variable on the proximal predictor at different levels of the contextual predictor. Okay, so we looked at similar plots earlier, but we just used arbitrary values rather than the mean and plus or minus 1 standard deviation. Of course, we could say those are kind of arbitrary as well. Why not use any other value? But at least they're based on some statistics. Okay, so how do we get these simple regressions? So here is our regression formula just taken from the output. So we got our intercepts, we put that down here, coefficient for extroversion, coefficient for number of people talked to, and then coefficient for the interaction term. So getting these simple regressions is, I think, quite simple. So, there's a little bit of a learning curve, but really there's not a whole lot to it. The value of extroversion we want to know about is its mean. So we centered extroversion at its mean. So we know that this is extroversion at extroversion equals 0. So we substitute 0 into this regression equation right here. So put that in for extroversion. And then that reduces to just this value and then this right here. So this is 0, multiply that by 0, multiply that by 0. It all becomes 0 and drops out. So this becomes our simple regression formula for predicting satisfaction with social life from number of people talked to at the mean level of extroversion. So note that we can get this all by just looking at these two coefficients right here when we've centered at the appropriate values for the proximal predictor. Okay, so at the mean in this case. Now let's look at a high value of extroversion. So when it's centered at the mean plus 1 standard deviation. Okay, so there's our formula there. We know that we want now the value of extroversion we want to know about is its mean plus 1 standard deviation. This is what we centered extroversion at. So this is at extroversion equals 0. We just substitute 0 into this equation, and it reduces to this. So there's our simple regression for predicting satisfaction with social life for number of people talked to at a high value of extroversion, the mean plus 1 standard deviation. Okay, and then here's our regression equation now with the extroversion centered at the mean minus 1 standard deviation. Okay, so now we can substitute 0 in here since we centered at that value, and it reduces to this right here. So there's our simple regression formula or equation just for predicting satisfaction with social life or number of people talked to at a low value of extroversion, 1 standard deviation below the mean. So we can plot these simple slopes using Excel. At the end of this lecture, I'll also show how to plot them using R. which is what I now use and what I recommend more than Excel. I actually think it could be a little easier than plotting them in Excel, but I don't know. I know some people really like Excel and don't want to get too involved in R yet. So what you need to do is first you define the range of the proximal variable. So say number of people talked to that we want the plot to cover. Then we give Excel the regression equation so it can calculate predicted satisfaction with social life at each end of the range. And then we ask Excel to make a scatter chart with lines connecting the two values at the ends of the range. So basically we're going to make two dots, one at each end of the range, and then we're going to connect those dots with a line, and that'll give us our simple slope line. Okay, so if I was doing this in Excel, I would get my simple slope formulas for each value. So this is a simple slope at the mean. And then the scale for number of people talked to had about 14 points. So we span it from -7 to 7 when it's mean centered. Okay, so there's our range of our proximal predictor. Find the predicted value for the simple slope at the mean of the context predictor. Okay, so use a simple slope regression formula. You would find this from like SPSS output. This is our simple intercept, and then our simple slope for number of people talked to, times this value in A5. So this is getting a predicted value at 7 people talked to, basically. Okay, and then we repeat these for the simple slopes for the mean +1 standard deviation and the mean -1 standard deviation. So note that here in these formula bars, you have to type in the formula for using the coefficients from when the model, when extroversion was centered at the mean +1 standard deviation, and then for this one, when extroversion was centered at the mean -1 standard deviation. So these will have different simple slope models, and then you just plug in number of people talked to. And then you ask Excel to insert a scatter chart using the simplest template. So you would go up to here, insert, and then pick scatter, and then define each of the columns of Y predicted values right here as a series to get one line for each simple slope. So this would be a series. It would give you one line connecting 2 points. This would be a different series connecting another one line with 2 points, and then the same thing here. So this is what you can get if you plot this in Excel for extroversion at the mean. There's our simple slope line. For extroversion at a high value, the mean +1 standard deviation. Okay, you can see it's a little bit steeper. And then for a low value of extroversion centered at the mean -1 standard deviation, there we get that simple slope. So it's a lot shallower. So you can see kind of the tilt or the slope of these lines increases as you get to higher levels of extroversion. So this is a similar approach to what we used when we got simple slopes in a polynomial model. So this is our example we talked about earlier, predicting test performance from anxiety. Here's anxiety at the mean. Okay, and then there's anxiety at the mean +1 standard deviation, anxiety at the mean -1 standard deviation. In a polynomial model, it's easy to see where the simple slopes touch that overall regression curve. Okay, so it's very intuitive and pretty easy to see. It's much more difficult to see an interaction, see this in an interaction model because the regression surface is a plane in a 3-dimensional space. That's with 2 predictors. When you get more than 2 predictors, of course, it's a plane in a multi-dimensional space, which is really hard to visualize. Okay, so in a 2-predictor model with no interaction, the regression plane is flat. You can think of it as being rigid like a piece of wood. Okay, so hopefully, most wood isn't warped or bent too much. In a 2-predictor model, though, with an interaction, the regression plane can be warped. You can think of it as being flexible like a piece of paper. So if you have a piece of paper, you can take it and you could stretch it to where some of it is kind of flat, and then the very end is kind of steeply pointed up. So that's kind of what we can think of as visualizing a regression surface with 2 predictors and an interaction. So the degree of warping depends on how big the interaction effect is. So the larger the effect is, the more warping there will be. Okay, so here's the regression plane with no interaction. So this is from this equation right here. So just the model just as a multiple regression model with no interaction. So there's extroversion from low to high, number of people talked to from low to high, and satisfaction with social life. So you can see that the plane is rigid. Okay, it's flat and it's not warped. Okay, so if we look at it like that, it's all kind of like one piece of plywood that's just tilted in a different direction. Okay, very nice demonstration, I know. This is very exciting. Okay, so moving on to regression plane with an interaction. Now here's our interaction equation. Okay, and then this is the regression surface. So you can see that it's a little warped, so the same thing as we just looked at. So the plane is warped. The near corner is pulled down slightly. So this one is pulled down slightly. This is the same result, but with the interaction exaggerated to make it easier to see. Okay, so you can see that it's kind of warped. It looks more like a piece of paper than like, say, a flat piece of plywood or something. Okay, so you can see the warping there. Okay. But really, you know, we don't have space in our papers to print out these rotating three-dimensional models. So really what we do instead is we use that simple slope kind of method to plot the effect between one variable, the proximal predictor, and the outcome variable at different levels, centered at different levels of the contextual predictor. Okay. So in terms of lower order terms, just like in polynomial regression, when we have a higher order term like an interaction, when that's included, all corresponding lower order terms have to be included. So when we have an interaction term x1 times x2, we have to include x1 and x2 separately. If the lower order terms aren't included, then the effects for the higher order terms will conflate the two or more effects and give an incorrect estimate of the effect we want. Okay, so because a higher order term requires any lower order terms also to be included, a hierarchical regression with an interaction has to work from lower to higher order rather than from higher to lower. Okay, so that order is okay. So say if we were doing a hierarchical regression, we first wanted to test like just the multiple regression model with no interaction terms. We might really genuinely want to test this. A lot of times it's good. A lot of times you might even want to start with just each term by itself, just to, for example, that's basically looking at whether there's a correlation between each term and the outcome variable. But you could start with this, and then in the second step you add the interaction term. That would be fine. But you couldn't do this, so have just the lower order term for predictor 1, and then interaction term, and then the second step add the lower order term for predictor 2. That order would not be okay. Okay. So like for polynomial regression, the automatic standardized regression that SPSS and JASP performs is wrong when the model has an interaction. So in the standardized results, we want standardized variables for lower order effects and the dependent variable, and then higher order effects created out of standardized first order effects. Our higher order effects, we don't want them to be standardized. But SPSS again has trouble because it doesn't know what that interaction term x1 times x2 is. It just looks like another variable. So not like a special case where it was a product of two other variables. So what SPSS does is standardizes y, x1, x2, and then x1 times x2. What we need to do instead is standardize all three variables, the outcome variable and the two predictors, and then compute that interaction term from the standardized lower order predictors, but don't standardize it itself. Okay, so I'll show the steps at the end. And then of course, if we've done this, we've manually standardized all the variables, then we just look at the unstandardized coefficient results. Okay, we could also add more predictors to the model. So that's perfectly fine. It just becomes a little bit more complicated. So say now we have this model, so we looked at that interaction effect, and then we also added two other predictors. So we could have had different reasons for adding these. Maybe they're nuisance variables, things we just want to control for, things we're generally interested in looking at, but we don't predict an interaction. So the interaction effect and simple slopes are partialed for these additional predictors. So the coefficients for the additional predictors are not unconditional because the predictors are not involved in an interaction. Okay, they are unconditional. So this is the same as when we added additional terms to a polynomial model. So regression can include three-way interaction terms and higher order interactions. We won't really get too much into those in this course. Okay, but you could have something like this. So this would be the simplest three-way interaction model. So we have all of our lower order terms, all of our two-way interaction terms, and then our three-way interaction. Okay, so the rule about including lower order terms still has to be followed. Of course, the power to detect effects typically drops with increasing order, so we don't often look at them. Actually, the power to detect effects really drops kind of exponentially just by adding an interaction term. If you want, Andrew Gelman posted a blog post about this a couple years ago that's really good. I think basically showing that you need about 16 times more power, or I think more subjects basically, to detect a significant interaction as compared to just significant effects in a main effects model. Okay. In regression, the inclusion of interactions is also typically driven by theory rather than being done by default, like in ANOVA. So typically, we usually have a good reason for testing interactions, not just by running it by default. A lot of times what you do if you think there's an interaction, hopefully you have a good reason for thinking that. You then add the interaction term to the model. If it's not significant, and especially if it's not anywhere close to being significant, you probably just want to drop the interaction term out of the model and just proceed with like a multiple regression model without an interaction term. So regression would also allow for polynomial terms and interactions to be combined. So this is an example of a model where we have our lower order terms and an interaction term. Then we have a quadratic term for predictor 2. And then we have an interaction term between predictor 1 and the quadratic term for predictor 2. Okay, so quite a complex model. Okay, so we still need to include all lower order terms. So now we, in this one, we have both the lower order term for x2 and the quadratic term, and then we have that included in the interaction between the quadratic term and the predictor 1. Okay, so interpreting these more complex models will follow the same principles we've discussed, but just more complicated applications of them. So you might have to think of different ways to, say, report these, different simple slopes to look at, and things like that. So the textbook, so the Cohen et al. Textbook discusses some of these models if you want to read more about them. So, it's probably only particularly useful if you think you'll have data like these. So we won't discuss these much more in class. Okay, so now let's move into doing some examples. So first we're going to do some examples with SPSS, for those of you still using SPSS. So first we ask SPSS to give us descriptives for our different variables. Okay, and then there we go. So we got the descriptives. So now that we have these, we can compute our different centered variables and then different interaction terms from those. Okay, so center extroversion and number of people talked to at their means. Okay, and then we make our interaction term. Okay, and then center extroversion at the mean plus 1 standard deviation. So I'm calling this A extroversion for above extroversion. Okay, of course you can call it anything you want as long as you keep it straight. Okay, and when we do, note that when we do this in R, we can really compute these means on the fly basically. So we don't need to do the kind of these steps up here. I don't know if I'll do that in the example today, but we could definitely do that if we wanted to. And then finally the B extroversion, so this is below the mean, so center at the mean of extroversion minus 1 standard deviation. So again, we're just getting the means from up here for extroversion, the standard deviation as well. And then there's our interaction. Okay, so now we have these different variables. And then finally, the last thing we need to do is create our z-values. So these are for the standardized scores. So take extroversion, subtract the mean, divide by the standard deviation. Do the same thing for number of people talked to. And then create that standardized interaction term. Okay, so we call it z, kind of give it a prefix of z. And then finally, when we're doing standardized regression, we also need to standardize the outcome variable. So let's standardize that as well. And then you can see I'm getting all of these from up here in this descriptive statistics table. Okay, so do all of that. And of course, like I'll mention in a minute, you could do all of this in like a spreadsheet editor if you wanted to, like in Excel, and then paste it into SPSS, or save it as a CSV and use it in JASP if you wanted to. All right, so here's our regression with an interaction. Okay, so first one's centered, and then this is centered with extroversion above the mean, number of people talked to centered at the mean. Okay, and so of course be sure to change the interaction term to match the variables being used. So, you know, there's a lot of steps here to get something wrong, and it could throw off your whole analysis. So it's important to always check and double check your work. You'll be surprised at how many mistakes you made, and you'll always continue to make them. I make a ton of mistakes. And so you'll be surprised at how many you make and how important it is to check over this. Okay, and then these are our last two models. So extroversion centered at the mean minus 1 standard deviation, and then our standardized regression. Okay, so be sure to change the dependent variable to its standardized version. So that's something that's different than in those other models. Okay, so the overall results, R squared and its F-test are the same across different centering and standardizing. And then extroversion is centered at its mean. Number of people talked to is centered at its mean. Okay, extroversion centered at its mean plus 1 standard deviation. Number of people talked to. Okay, so we've already looked at these coefficients earlier, so we've looked at these results already. So a slope of 0.546 when extroversion is centered at the mean, whereas a slope of 0.811 when extroversion is centered 1 standard deviation above the mean. Okay, so only B2 changes because only X1 is changing its 0 point between these two regression models. Okay, standardized coefficients, we don't want to look at those. Okay, we'll look at those when we do just the standardized model. Here's the model with extroversion at its mean minus 1 standard deviation. Okay, and then here's the manually standardized model. Okay, so again up here we can see, we already looked at this, but a much weaker effect of number of people talked to in predicting satisfaction with social life at a low value of extroversion. Okay, and so again, to get the standardized results, we look at the unstandardized part of the manually standardized model. So this gives us, say, the standardized effect for the interaction term. Okay, so don't look at those standardized coefficients. So regression models with these interaction terms can also be performed by first creating the interaction terms and then the centered variables, things like that in Excel. Okay, so for several years I kind of used that approach. This basic approach is similar to polynomial regression. I think it could be preferable, particularly if you're starting out, to kind of do some of this stuff in Excel to diagnose errors and be clear on what transformations you're performing. Of course, the flip side of that, you might just want to start doing everything in a script, like in R, because then you can kind of go back and see, you know, where you made the mistakes. It might be harder to kind of spot mistakes in R, but it might be harder to really know that you are making a mistake in Excel, because you can't quite see the formulas and things like that as clear as you can in R to make sure everything conceptually lines up. Okay, so the most important thing though is to just check your work and check the plausibility of your results. So again, You're getting a PhD, you're going to be an expert, so there's no one else to ask. So you have to figure out ways to make yourself assured that you have done everything correctly, you've checked it, and it is competently done, and you're the expert, you're the one kind of making sure that it's done right. Okay, so you might not be in that mindset yet, but I think it's good to kind of develop that mindset eventually, and hopefully, you'll eventually acquire that expertise. So now let's move to a JASP example. So we'll do a JASP example and then an R example, and then that'll be it for today. So open up the Byrne, Norris, Worthy data set in JASP. Okay, so in this study, this was a study published a few years ago, spontaneous eye blink rate, so it's going to be denoted as EBR, was used as a metric of striatal tonic dopamine. So there's been some work recently been done looking at this. It's a little bit controversial. I think a couple of PET studies failed to find like a very clear relationship between dopamine and as measured by their methods using PET and spontaneous eye blink rate, but a lot of other studies have found kind of correlations between spontaneous eye blink rate and behavior. So what we found in this study was that EBR interacted with CESD depression scores to predict decision-making performance in the Iowa gambling task. So it's interesting. So the Iowa gambling task is a task where you choose between 4 decks and you can get gains or losses on each trial. And so in a lot of ways, it's kind of a loss minimization task because you have to figure out which one of the decks lead to the big losses. And so we actually found in some cases here, it's an interaction, but in some cases we found that depression was associated with like better performance on the task. Presumably, some of our prior work suggests that depression may make people more sensitive to losses, and so that was kind of the putative reason we saw this effect. So here, if you have it open in JASP, click on regression, and then linear regression. Enter performance as the dependent variable, and EBR, CESD, and then EBR times CESD as covariates. Okay, so real quick, I'll just show you what the data set looks like. So this is a case where I've actually computed the interaction terms themselves beforehand. So we have EBR, CESD, and then performance, our main dependent variable. Okay, and then we have the interaction term. Then we have EBR centered at the mean, EBR minus 1 standard deviation, EBR plus 1 standard deviation, and then CESD centered at the mean. Okay, so basically our proximal variable here is CESD. We're interested in what is the relationship between depression and decision making, and then EBR is our contextual variable that we're centering at different values. So then I have the mean centered values at the mean for each variable, at 1 standard deviation below the mean for EBR, and then at 1 standard deviation above the mean for EBR. So I created all the variables first in Excel. I don't have the formulas here because this was saved as a CSV file, but originally we did this by doing formulas in Excel. And so now I have it saved as a CSV, and I could just open it in JASP. I could also just copy, this data into SPSS if I wanted it. And I think SPSS has a way to open a CSV file as well. Okay, but back to this example. So that's just to show you like what the data will look like, and you can open that file yourself if you want to. Okay, so here we look at this and we see that there's a significant interaction, just significant interaction, p equals 0.043. So it's not an extremely small p-value, so enter the same variables in a Bayesian linear regression. Okay, and so I think this is doing something kind of like conflating the lower order values, but you can see that most of the model is just in the interaction term. Okay, but then there's Bayes factors that warrant the inclusion of the full model as well. Okay, so this is actually with the multiple, so this is like the full model. The base factor for including the full model is 7.275. Okay, so it appears that there is at least a good amount of support for including the interaction. Some people view this differently. I think with an interaction, if there's kind of even moderate support for including it, you might at least want to look at that and interpret the results, even if they're not the strongest effects ever, if it appears that there might be an interaction. Okay, so it looks like there's a significant interaction, so we will center EBR at its mean, +1 there's standard deviation, and -1 standard deviation, and then just center CESD at its mean. Okay, so the coefficient for CESD is going to tell us the effect of performance at low, moderate, and high levels of EBR. Okay, so tell us the effect of this depression scale and how it predicts performance at those different values for EBR. Okay, so now go back to regression in JASP, click linear regression, and then enter performance as the dependent variable. Okay, an EBR centered mean, CESDC mean, and then the interaction term between the two variables centered at the mean as predictors. Okay, and then this is what we get right here. Okay, so the interaction coefficient should remain the same. So the coefficient for CESDC mean is not significant, indicating that depression does not predict performance at the mean level of EBR. Okay, so now remove those covariates and enter EBR centered at 1 standard deviation below the mean, and then CESD centered at the mean. Okay, so we again have the significant interaction, but if we look at the coefficient for CESD C mean, okay, it's not significant, indicating there's no relationship between depression and performance for individuals low in EBR either. Okay, so far, we haven't found anything significant. Okay, but now if we remove those and enter EBR centered at 1 standard deviation above the mean, CESD centered at the mean, and then the interaction term from those. Okay, so now the coefficient for CESD centered at the mean is highly significant. So for individuals high in EBR, more depressive symptoms predicted better performance. Okay, so in other words, if EBR is a proxy for tonic striatal dopamine, then having a higher value leads to a stronger relationship between depression scores and performance in this task. Okay, so P equals 0.001 in that case. So this is kind of similar of a couple other of these similar interactions we found between EBR and substance use. We found some of the least negative effects of substance use on reward sensitivity and things like that were for people higher in EBR. So there is one possibility that this kind of having high tonic dopamine might kind of insulate you from some of the negative effects of these other things like depression or substance use and things like that. Okay, so we've not looked at just the lower order coefficients, so we might want to do that. So enter performance as the dependent variable, and then EBR and CESD as covariates. Okay, and so CESD is a significant positive predictor. So the interaction suggests that this relationship is especially strong for individuals high in EBR. And of course, you could just look at the correlations between EBR and CESD individually and how they relate to performance as well. So this is like a multiple regression model. Okay, so even with EBR included in the model, there's still a strong effect of CESD. And then, of course, the interaction suggests that this relationship is especially strong for individuals high in EBR. All right, so that was our JASP example. Now we're going to do an R example with the same data set. So I'll now use the same data set and plot the simple slopes in R using ggplot2 from Tidyverse. We could do much more in R, like creating new variables centered at different values. I think we'll actually do a little bit of that. But here we're just going to focus mainly on plotting the simple slope. So these simple slope plots are kind of the most important thing to help visualize your interaction effects if you ever have data that you have an interaction with. And so it's also a little bit counterintuitive, so that's what I wanted to go over in this example. So open up the continuous interaction.r script. Okay. So this is what it should look like. Change the path in lines 1 and 7 to wherever you have the Psych 671 rstats folder saved. Okay, so mine is in just this folder called rcode on my C drive. And then I changed this line 7, so now if you're in that directory, it'll just look within that folder. So that / will tell it to look within the current directory for this data set right here. Okay, so once you have these lines changed, and of course if you want to set this directory, you could look at what you set it to in one of the prior scripts, like for multiple regression that we went through a few weeks ago. So we'll just be using the first 3 variables in this case. So we could use mutate to create any new variables, or we could use that money sign as well. That I've talked about in some prior lectures. All right, so run lines 10 and 11 to run the model with an interaction. Okay, so by using the star sign, R is going to automatically create the interaction term between the 2 variables. Okay, so that's one thing I really like about using R. We actually didn't have to create that interaction term ourselves. It knows from the linear model command to test the interaction and include the lower order terms as well. Okay, so that's kind of nice, I think. Okay, so we can look at these results, and they should be the same results that we got in JASP. Okay, so point 0434. Now run lines 14 through 22. Okay, so these just create variables we'll later plug into the regression. Using simple slopes. So we're creating a variable for mean EBR, standard deviation for EBR. These just have R print out for you like what those are. So if you ran just this part, you would get those. And then mean EBR minus SD, mean EBR plus SD for plus and minus 1 standard deviation. Okay, so all pretty simple, and using these up here. And then mean EBR, that's just printing them out. Okay, and now run lines 28 right here through 45. Okay, so this will do a lot of stuff. So first we name values for each coefficient in lines 28 through 31. So basically we got these from M1. So M1 was our linear model up there, a few lines up that we ran. So we saved it as M1. Now we call the coefficients from M1, which is now our output object for that model. Call coefficient 1 as B0, coefficient 2 is the coefficient for EBR, coefficient 3 is the coefficient for CESD, and then coefficient 4 is the interaction. So I'm just labeling these to put them in below. Okay, and now I write the algebraic equation representing the results of this analysis 3 times. Okay, so the first time we write it in standard form. Okay, so print performance equals that. Okay, and then write out the regression with EBR as conditional. The slope is proximal, and CESD is the context. So this is just like what we did in the last lecture, but now we're doing it in R basically. Okay, so B0 plus B EBR. Okay, the quotes just represent like what it's actually gonna like what font is actually gonna be displayed. Okay, or text is actually gonna be displayed, and then if it's without font, then it's referring to like one of these up here. Okay, plus CESD. Okay, and then write out the interaction in the other way. So basically, these just write out the interaction model in different ways. Okay, so now run lines 50 to 57 to show all 3 simple regression lines in the same plot. Okay, so we did this using geom AB line. So that creates a line basically, and then entering the slope and intercept from the rearranged regression equation. Okay, so here's we're calling ggplot our data. X equals CESD, Y equals performance. Okay, so we're plotting performance as a function of CESD, geom point. Okay, so that's giving us just the scatter plot that we're going to overlay, so giving us all the data points. And then geom AB line. Okay, so this gives us the intercept equals B naught plus the mean EBR, okay, times B EBR, and the slope equals B CESD plus mean EBR times the interaction. So all of these are in that slope intercept form, and we're just calling those actual values that we computed up above. Okay. And then this is the second line, so mean EBR minus 1 standard deviation. So this will be plotting the slope when EBR is centered at the mean, and then when EBR is centered at the mean minus 1 standard deviation. Okay, and then when the EBR is centered at the mean plus 1 standard deviation. Okay, and I think this example, I got it from another place. So if you look in the script, I'm not sure, I may have talked about it somewhere. I know I wrote in a reference in the script for where I got this, the basis of this example from, and adapted it to this data set. So you can look at that if you want for more details. Okay, and then finally on line 50 we have R show the scatter plot for performance by CESD. Okay, so this is kind of what I was just going over. Then in line 51, we enter the slope using the coefficients we have computed along with mean EBR. Okay, then we plot a similar line but entering mean EBR minus SD and mean EBR plus SD for the value of EBR in the regression equation. Okay, and then we get this nice graph with the 3 simple regression lines plotted. Okay, so you can see over here the green line, plus 1 standard deviation for EBR. Red line, 1 standard deviation below the mean, so almost flat. And then kind of a shallow slope for the mean EBR as well. Okay, so now we have our plot. We could add a title to this or change other aspects of the aesthetics if we wanted to. Okay, I won't do them here for time. But if you look in some of the earlier R scripts that we created, it's going to be similar similar code for that. So the plot makes it very clear that there's a stronger effect of CESD on performance for higher levels of EBR. Okay, so we couldn't really get that as clearly in any other way. If we plotted the regression plane in that 3-dimensional, we might get something like that. But I think I still don't think this would leave us as clear as clear of impression of the data as we have now. Okay, so one last thing that I want to mention is that the BRMS package, which I highly recommend downloading and learning how to use, it's basically Bayesian versions of both the linear model command and the LME4 package for mixed effects regression. It has a really cool command called marginal effects that by default plots the lower order effects as well as simple slopes at the mean plus minus 1 standard deviation. Okay, so you could run lines 64 through 68. It should take a little longer, and then the marginal effects command will show you first the marginal effects and then ask you to press enter to see the next 2 plots. So I actually ran this. It just took about a minute, really. I thought about running it in this video, but then decided didn't want to even do that. But so I ran this. So I changed this line because this is how you can get the summary to print multiple digits. So this was the default summary. It only prints to 2 digits, but I find a lot of times I need to print to more than 5 digits. So right here in line 66, I have it print out 5 digits. Okay. So what you're looking at here, so these are Bayesian models, so it doesn't give us a p-value, but what you can do is you can look at the estimates, which should be the same or similar as the coefficients you would get from the linear model. Okay, and then what you can look at, in terms of seeing if it's like significant or different from zero is you can look at, this is the lower bound of the 95% credible interval, and then this is the upper bound of the 95% credible interval. And so you can look and see, does that credible interval, does it include zero? So it includes zero for the intercept, for the lower order term for CESD, and for the lower order term for EBR. Okay, it doesn't include zero for the interaction term between CESD and DBR. Okay, so that's kind of how you can do a proxy for like a significance test, basically. So these are the population level effects. So we do have a significant effect. Now, one thing I like about BRMS, and one thing I think it's really good to just learn how to use, because it's really kind of the simplest way to plot effects in a lot of cases. You can just run a BRMS model, and then so this is, I saved it as M1 BRMS. So there's our model output file. And then what you do is you run this marginal effects. Okay, so tell it to give us marginal effects. So that it'll give the lower order effect for CESD on performance. Okay, so there actually is a lower order effect here, just a general kind of correlation. Okay, and then the lower order effect for EBR on performance, there's kind of a mild positive correlation as well. Okay, and then it'll show you the simple slopes at different values. Okay, so what's nice is it automatically centers these at the mean value for EBR and then at the at plus or minus 1 standard deviation. So what BRMS does, it assumes that the first predictor that you enter is the proximal predictor, and then the second predictor is the contextual predictor. So that's why it's automatically plotting this as the relationship between CESD and performance at different levels of EBR, the contextual predictor. Okay, so you can see the similarity between the plot we created. Where did it go? Right there. Okay, and then the plots, the simple slope plots that that BRMS creates. Okay, so this is actually nice because you could just run this model and then you could automatically get these plots, and so it could be like a first pass at your data essentially. That could be quicker than running this interaction and plotting the results manually. So I really like this marginal effects command from BRMS. Okay, and then we can verify. So we already computed, if we look up here, we computed mean EBR. So let's see what it is. Mean EBR, 17.8. Okay, and so that's what we get over here, 17.8. Okay, let's look at mean EBR minus 1 standard deviation, 9.46. And we see 9.46 here. So this is all a nice feature of the BRMS package. Okay, so this is almost it for today. Okay, so these are our results that we got from that marginal effects command. Okay, so I have an interaction, or an interaction. I have a poem that I was inspired by all this stuff on interactions to write this poem. So two predictors combined in a GLM to make their effect not additive. B3 could be interpreted then as change in slope for either of them, but which interpretation should I give? I knew convention, yet I chose to defy the approach that others always used. Two predictors combined in a GLM, and I gave the interpretation less chosen, and my paper was rejected. So thanks to Robert Frost, this was, from his long-lost catalog that that was recently found. Okay, so not really. So that's it for today, and then next week we'll start talking about interactions between continuous and categorical variables. All right, thank you.